When you think of calculus, what do you usually think of? I'm sure most people think of mathematical equations or STEM, and more specifically, engineering careers. Some examples that come to mind are usually people like Elon Musk and his work with SpaceX rockets. And although those are all perfect examples, there are so many other ways to use calculus outside of building rockets and the genre of engineering as a whole. My presentation today is to educate and inform you on calculus and its lengthy relationship with outer space. Examples of mathematical astronomy have been found in surprisingly early time periods. In the 1800s, almost completely intact tablets were unearthed from an archaeological dig in what is now modern-day Iraq and were placed in the British Museum. The clay tablets were found with cuneiform writing, and in early 2016, a study showed that they were from Babylon. Cuneiform writing is an ancient alphabet that was used in Mesopotamia, Persia, and Ugarit, and dates back from the early Bronze Age to the beginning of the Common Era. The writing detailed integral calculus to calculate the path of Jupiter. Sadly, I can't read the text myself, so I have to trust the archaeologist on this one. Now, I know what most people think. It just sounds like another boring discovery, but this was actually a big find for archaeologists. That's because integral calculus had previously been thought to be invented in medieval Europe, which is about the 14th century, but these tablets were found to be made in 350 to 30 BCE, meaning the Babylonians invented this math about 1400 years before the Europeans. That's quite a bit of time. I wouldn't let Isaac Newton or Gottfried Leibniz hear about this. Anyways, they actually first applied this math to physical objects, such as land or buildings, but later used the math to track Jupiter's path to understand the will of their god Marduk, the god of creation. This was to predict future grain harvests. Alright, that's enough of the history lesson. The main idea of this is to show that calculus is used in a lot of astronomy to describe the motion of celestial objects and forces. For example, an asteroid's velocity can be found using a differential equation. I'm going to take you back in time to solve Jupiter's velocity, just like the Babylonians did. We want to find the velocity of Jupiter with respect to time. Our God has told us the rate of change of velocity over time is equal to a constant times 3v plus 10, and that the velocity at time 0 is 30 kilometers a second, and at time 4, the velocity is 20 kilometers per second. Some data that we know is the velocity has to be greater than 0 because Jupiter is in motion. First, we're going to multiply dt to both sides, and then divide 3v plus 10 on both sides to be able to integrate the equations. To integrate the equation on the left, you can do u sub, and you end up with 1/3 natural log of 3v plus 10 plus a constant. And the result of the integral on the right is kt plus a constant. If we subtract c from both sides, we get a new constant. Next, we multiply both sides by 3 to isolate the natural log, and a constant times a number just gives us a new constant. To cancel the natural log, we make each side powers to e, and because we did this to both sides, they're still equal. This gives you 3v plus 10 is equal to e to the 3kt times e to the c. And e to the c can be rewritten as a new constant, which makes the new solution ce to the 3kt. To isolate the v, we subtract both sides by 10 and divide both sides by 3. And as we rewrite c over 3, we get v is equal to ce to the 3kt minus 10 over 3. Using our given data, we know if we plug in 0 for t, then v equals 30. And solving for c gives us 100 over 3. Now we're going to find our variable k. Using the data that v of 4 equals 20, we can say that 20 kilometers per second is equal to 100 over 3e to the 3kt minus 10 over 3. But because t is 4, we can rewrite 3kt as 12k. So next we can multiply both sides by 3 to cancel out the fractions. Then add 10 to both sides and divide by 100. Next, we take the natural log of both sides to cancel out the e, and we get the natural log of 7/10 equals 12k. Then we just divide by 12, which gives us k equals natural log of 7/10 over 12. This is approximately negative 0.030 when rounding to the nearest thousand. Now we just plug in our values. So our c equals 100 over 3, our k times 3 is negative 0.089, and we subtract 10 over 3. In the solution, I rounded everything to the nearest thousandth. And that's it. I'm glad we have these equations nowadays, because without these techniques, if an asteroid threatened to hit Earth, it would probably look like this. Or like this. To sum up this presentation, we can use calculus and more specifically differential equations in regards to space and not just building the transportation to get there. Thanks for watching!